Welcome back, learners. You know, in the previous lecture, we were just doing the Excel sheet design, right? So we have completed up to the factored bending moment value, right? So once the factored bending moment is done, your next step is finding out the effective thickness of the footing, right? You have to find out the effective thickness, that is nothing but your effective depth of the footing, right? Your next procedure or the next step is to write the Excel sheet formula to get the effective thickness, okay, or the effective depth of the footing. So in order to do that, you can see here that I need this value and divided by this value. So first let me write this value, right? So when I write this value, I can show that is equal to two columns I will put, right? So first is my bending moment at the critical section, which is in kilonewton meter, that I have to convert it to Newton mm, so that I have to multiply this by 1000 two times, right? So that will convert your bending moment at the critical section, which is in kilonewton meter, to Newton mm. So divided by, so what is the formula? The formula is 0.138 FCK 1000. So therefore I have to choose 0.138 that into FCK into 1000 into 0.138, right? I will close the bracket. So that will give the value of the top load, that is this value. That value, it has to be squared under square root. Therefore again when I do that, I will get my overall thickness or depth of the footing in D, okay, in mm, right? So overall depth, sorry, not overall depth, the effective depth of the footing. So therefore let me give effective depth of the effective depth of the footing, which will be given in small d in mm, right? It will be equal to SQRT square root, so square root of this bracket, this cell, that will give you the effective depth of the footing as 188.9713 mm. So for that, what you have to do, once you get the effective depth, your next step is to calculate the overall depth of the footing by adding the effective cover, right? So therefore let us give effective cover to the footing, effective cover to the footing, which is usually given as D dash, which will be in mm again, okay? So that is an input value, we have to give it as 50, right? That is an input value, we have to give it as 50. Therefore let us make it as italic and green. So then after that, I will get the overall depth of the footing, okay? So overall depth of the footing. So overall depth of the footing will be given by capital D, and that will be in mm, and that I can give as equals to, right? So this plus this, so that will give you overall depth. And you know, again when we have done the calculation of your longer dimension and the shorter dimension, so what we have done, we have rounded off the longer dimension and shorter dimension of the footing to the next number. In the same value, here also we have to round it off to the next higher value, that is, I can write final overall depth of the footing I can make, okay? So final overall depth of the footing, I can make it as D, right? D final, which will be in mm again. So I have to give that value as, like for example 250 mm, like that. I have to round it off to the next higher number, right? So this will be my bold italic green as well as this one, indicating that it is an input value as well as the final value. It is an input value as well as the final value, right? Yes, that's the reason I made it like this, right? Okay. Right? Okay. So that is your final overall depth of the footing, d final in, that you got it now. So once you get the overall depth of the footing, the next step is you are finding out the area, finding out the reinforcement details. So in order to do that, you need the value of mu by b d square value, right? That is factored bending moment at the critical section divided by shorter dimension of the footing into 1000 into overall depth square, right? So therefore what I have to do, I have to give that value, and there will not be any value of mu by bd square, right? The next step is calculation of mu by b d square. Okay, so no unit for that, so you can give this itself like this, right? No unit for this, right? So no unit for this, so I have to calculate now. So there will not be any unit for this. Okay, yes, so there will not be any unit. So now I have to calculate mu by bd square. So therefore what I will do, I will keep first mu, that is factored bending moment, right, into, I will make it 1000 two times because I need to make it into Newton mm. So divide by, what I have to do, I have to first shorter dimension of the footing, right? So shorter dimension of the footing means that is 1.5, that multiplied by 1000 into overall depth square, that is your 250 into 250, that will give you your mu by bd square value 1.97. okay, 1.97, right? Yes, and one more thing, when I found out the effective depth of the footing using this formula, effective square, I just wanted to know which, yes, I have to use factored bending moment, that is D column 22 I have used, instead of that I have to use 23. okay, I'll just remove it and I will make it this one. okay, yes, so now you can see effective depth 230, so 50 cover 281, so I can make it as 300, right? Yes, so you are getting 1.36. so that will be your calculation of mu by bd square. So once you get the mu by bd square, you are supposed to go to the SP16 chart, right? You are supposed to go to SP16 chart. okay, yes, supposed to go to SP16 chart. So in SP16 chart, so what I have to do, I have to go to the table. Let us see now. Yes, this table, right? So I have to use the grade of concrete 25. okay, this is for the slabs. oh, this is not this one also. For columns, this one I think it is in the beginning only. Yeah, this one. Yes. So I have to use for the FCK as 25. Okay, I have to use FCK as 25. Now what is my value of mu by BD square value? It is 1.36, right? So you can see here approximately 1.36. I can make it as 1.35, no issues. So for FE415 grade, right, that is, you can see 0.401. So 0.401 is my area of the steel, that is percentage of the steel required. 0.401 is always, it is greater than 0.12%. So therefore I can write in the next step PR percentage of the steel, percentage of the steel required, we given in PT and no unit, it is percentage. Okay, it is percentage. So it will be how much? The value will be 0.401. Okay, it will be 0.401%, and this I am writing, right? So it should be italic and green, and keep it in mind, this should always be greater than 0.12%. This should always be greater than 0.12%. It cannot be more than 0.12%. So once you get the percentage of steel, then you can calculate the area of the steel per meter width of the footing, right? So it is area of steel per meter width, right? So that will be area of the steel per meter width. I can give it as A ST. It will be mm square, right? So how will you calculate the area of the steel per meter? It is percentage of steel into 1000 into your overall depth by 100, right? I can write percentage of steel, that is this one, into 1000 into your overall depth divided by 100 will give you my area of the steel for per meter width. Okay, area of the steel per meter width. Okay, so that will be my area of the steel per meter width. Okay, yes. So this is an, again it is not an input value, it is a calculated value. So once your area of the steel per meter width of the footing is done, then you have to find out what is my diameter of the bar that I am supposed to use in the footing. I told you, when we are doing a concentrated, that is concentric isolated footing, we take the diameter of the bar used both parallel to longer direction as well as shorter direction, same, we don't change it. So therefore I can give diameter of the reinforcement, right? You can give the diameter of the reinforcement, right? You can give the diameter of the reinforcement. So there is a specific symbol for the diameter, 5 usually we give it as. You can go to insert, in the insert you can go to symbol, and in the symbol you can find out that 5. Yes, you can see here, this is my actually the diameter 5. Okay, and it will be in mm, right? It will be in mm, right? So that is an input value. So let us take that I am providing 12 mm dia bars. So this is an again input value. Okay, yes. Okay, yeah. Yes, so that is the diameter of the reinforcement. So once you get that, your next step is you have to calculate the area of that one reinforcement, right? So area of individual reinforcement, area of the individual reinforcement, that I can write it as small ast, which is in mm square, which is equal to, right, it is 3.142 into this, that is pi into d square divided by 4, right. So that will be your area of the one reinforcement. So once you get the area of the one reinforcement, you can get the spacing, okay, you can get the spacing of the bars. So therefore what will be your spacing of the reinforcement, I can write it as S, okay, I can write it as capital S, and it will be in mm. That will be this divided by, that is the area of individual reinforcement divided by the total area into 1000, right. So that will be your spacing of the reinforcement. Now keep it in mind, student, your spacing of the reinforcement, okay, your spacing of the reinforcement, it is same as that of the spacing of the reinforcement in the slab, okay. So when you do the spacing of the reinforcement in the slab, you can see that whenever the spacing is done, your spacing should not be more than the 300 mm value, as well as it should not be more than 3 times the diameter, okay. So you have to give the minimum, okay, it should not be more than that value, right. The spacing of the reinforcement should not go beyond, it should not go beyond, whichever is smaller you have to take, either 300 mm or 3 times the dia, whichever is smaller you have to take that, okay. So you can see here that this value is less than 300 mm, as well as the 3 times the dia, that is it is more than this value, so therefore no issues, it is safe, okay. But keep it in mind, students, this reinforcement we are not giving in the footing, but just to make the problem here I am doing. For example, usually we maintain a reinforcement of 14 or 16. So when I do that, you can see my reinforcement spacing will be increased, okay. So just to develop the Excel sheet I am using, so we will see that what is the exact reinforcement we have to use later, right. So once this is done, so your reinforcement is also ready, right. Yes, so you can usually again you can round it off to the nearest lower spacing, therefore I can write final spacing of the reinforcement, I can give final spacing of the reinforcement, I can write it as S final, I can write it as in mm, so I can round it off to 150, okay. So say for example I am doing, so and this will be, it has to be bold, italic, it has to be highlighted, okay. Yes, okay. Yes, this is how it is. So once this is done, your main reinforcement, main designs is done, that is longer dimension of the column, shorter dimension of the longer dimension of the footing, shorter dimension of the footing, so your thickness, that is overall depth of the footing, then reinforcement details, everything is done, okay. So once this is done, your next step is you are finding out the check for the two-way or the punching shear, right. So let us do that. We have to check for the two-way or the punching shear. You can give the naming here, I will just merge it, I will give the naming two-way or punching shear, two-way or the punching shear, okay. Yes, to wear the punching shear. Now in that, what is my first step? I have to get the length of the punching influence plane, that is A0. Okay, the length of the punching influence plane, that is A0. Okay, so we have to find out length of punching influence plane, which is given as A0. Okay, in mm. Okay, sorry, it is not mm, it is in mm, right? Yes, it is the length of the punching, this one in mm. Okay, yes. So what is that? The longer dimension of the column into 1000 plus effective depth by 1000. Okay, the longer dimension of the column, which will be in mm. Okay, so we have already taken it is in mm, right? Okay, so or better what we do, we will make this in meters only, right? So that it will be easy for us. Longer dimension of the column in, let us make it in meters, right? That is 0.250, and the shorter dimension also we will make it, so both are in meters, let us make it 0.40. Okay, 0.40. So now I have to choose, what is the formula? It is longer dimension of the column into 1000 plus effective depth, right? So therefore I can choose longer dimension of the column into 1000 plus longer dimension of the column into 1000 plus effective depth, not overall depth. So effective depth of the footing, right? Effective depth of the footing whole divided by 1000, right? So I can stop here, divided by 1000. That will give you the value in meters, right? That will give you the value in meters. So I have to convert it into mm, right? So better what I will do, I will not do this divide, so that I will give the value in mm, right? Then similarly I have to calculate the shorter punching influence plane. Okay, to calculate shorter punching influence plane, that is, what is that value? It is my B0, right? It is my B0, right? I can write it as B0 and it will be in mm. So same here, I have to do, it is shorter dimension of the column into 1000 plus effective depth of the footing, right? So that will give you your shorter punching influence line. Okay, yes. So once you calculate these two, that is A0 and B0, your next step is punching shear force value, right? Yes, punching shear force. Your next step is to calculate punching shear force. In order to calculate your punching shear force, you have to subtract your punching shear value from the axial load, right? You have to subtract your punching shear value from the axial load. So in order to calculate my punching shear value, right, I have to calculate first punching shear value. So let me give that, right? Punching, punching, punching shear value, value, right? So no symbol for that. So my punching shear value, I have to get it, right? My punching shear value, I have to get it in kilonewton, right? So it will be in kilonewton. Then what is the formula I have used, right? What is the formula I have used? Q max into A0 into B0 by 1000, right? That is Q max, that is maximum pressure, into your A naught into B naught divided by 1000 will give you, right? So I need to do one more 1000, then only you will get, sorry, one second. Yes, so I will give the punching shear value in kilonewton. Okay, so Q max into A naught into B naught, right? Because you can see your Q max, that is maximum pressure, it is in kilonewton per meter square, right? Whereas your A naught and B naught, they are in mm. Okay, so therefore I cannot directly do that. I have to divide them by 2 times. Or what else, what I can do, if you have a doubt, then what I will do is I will go to this one, divide by 1000, I will close this, into, I will open one more bracket, this one divide by 1000. Okay, so if you have a doubt, I will close this bracket and, sorry, one second. Yes, so I will open one more bracket here, then that will close this bracket. So that multiplied by your maximum pressure, that is this one, then I will close the bracket and will give enter, that will give you the same value. Now it is clear to you. So that will be your punching shear value. Then once you have the punching shear value, then you have punching shear force, right? So punching punching shear force, right? So punching shear force will also be in kilonewton. So that will be your axial load. Okay, that is axial load on the column minus your punching shear value, that is this one. Okay, so this will be your punching shear force. So then your punching shear force, once it is calculated, your next step is punching shear stress. So how to calculate punching shear stress? Your punching shear stress is calculated by axial load into 1000 by this value in Newton per mm square. Before that, you calculate this value. Okay, so that is A naught plus B naught into 2 into effective depth, right? So let us calculate that value. It is, first I will put A naught plus B naught into 2 into my effective depth. Okay, my effective depth, right? So that will be one value, right? Okay, so now you go for the axial load into 1000. Now I will give you punching shear stress. So here it will be punching shear stress. It will be in Newton per mm square. So that will be your axial load. Okay, that is your punching shear force, right? So it is your punching shear force, that is nothing but this one into 1000 divided by this value, that will give you your punching shear stress, that is 0.850 Newton per mm square. And what is your permissible shear stress? Your permissible shear stress you have to calculate. My SSIB LE, permissible shear stress. Your permissible shear stress is also, it is in Newton per mm square. It is 0.25 into your SQRT, that is your square root of 0.25 root FCK, right? Yes, so that will be your permissible shear stress, and I already told you your permissible shear stress should always be higher than your punching shear stress, Your permissible shear stress should always be higher than the punching shear stress. It is there, therefore there is no issues. So once this is done, your next step is last step, that is one way shear. Okay, that is one way shear, right? So that will be your one way shear, right? Yes. So how to check for the one way shear? First you are supposed to calculate the shear force at a distance d from the column face. Okay, that is shear force at d from column face. Okay, so from column face, shear force at d from the column face. Okay, yes. So that is calculated by 1000 into that critical depth minus effective depth divided by 1000, because I am getting that answer in meters, right? So therefore, or if you don't want in meters, so let us keep it in meters. That is, it is 1000 into your critical distance, that is x. Okay, yes, that is 1000 into x minus, so I will close this bracket, minus your effective depth of the footing. Okay, so that will give you your answer in mm. So if you want it in meters, then again you divide by 1000, right? So that will give you in meters. So once you get that, you calculate shear force, that is critical section into Q max into B. Okay, critical section into Q max into B, that is whatever the distance you calculated, that into Q max into B in kilonewton, right? That is shear force, okay, which is in kilonewton. Okay, that will be given by this multiplied by, okay, this multiplied by your Q max, that is maximum pressure, right? So this one into B, okay, that is your breadth of the footing, right? That is the shorter dimension of the footing, that is 1.5. So that will give you the shear force value in kilonewton, right? Because you can see here, this will be in kilonewton per meter square, so this will be meter, this will be meter, that will give you in kilonewton. Then what is your shear stress? The shear stress will be the shear force into 1000 by B into 1000 into D. So let us calculate shear stress, which will be, I wanted that in Newton per mm square. So that will give you shear stress is equal to, I can make to this one, so this into 1000, okay, so this into 1000 divided by, what I have to show, I have to show B into 1000 into D, right? So why that 1000? Again to convert my footing from meter to mm, right? I have to choose the footing dimension, that is this one, right? So that into 1000 into my small d, okay, that is small d, that is effective depth, this one, okay, right? So when I simplify that, I am going to get shear stress as 0.630. Then next, last you have to have permissible shear stress, right? P-R-M-I-S-S-I-B-L-E, permissible shear stress, that is also, it will be in Newton per mm square, right? So how you get that permissible shear stress? Your permissible shear stress, you will get it from IS 456, right? you know your permissible shear stress should be again, right, your permissible shear stress should be again higher than your permissible shear stress should be again higher than your actual shear stress acting. Yes, now you are getting permissible shear stress, right? So permissible shear stress is getting based on this 100 AST by BD and grade of concrete. So right, you calculate 100 AST by B into D. So how you calculate that? I will just write 100 into, right, so AST divided by small b capital D, right? Yes, that is what it is. So again there is no unit, right? So how you calculate that? It will be 100 into what is my AST, that is the area of the steel required, that is this one, 100 AST divided by B is 1000 into what is my capital D, my final depth, overall final depth, capital D, right? So that will give you your 100 AST by BD value 0.40, right? So now by looking into that, just go 0.40 and M25 grade of concrete. Here 0.40 is not there, it will be 0.25 and 0.50. The next video I will tell you how to do the interpolation. So I can go to 0.50, but for 0.50 my grade of concrete is 0.49, right? So my permissible shear stress will be 0.49. I will just do one thing, I will just cut it here and I will just paste here. Okay, yes, so therefore it will be 0.49. You can see now, even my this is my enter value, I have to enter this, right? So therefore let me make this as green. Even here also I have to enter permissible shear stress. It is not a value obtained, it had to be entered. Your permissible shear stress should be higher than your shear stress. You can see it is not higher, right? It means it is going to fail. So therefore what you have to do, you have to increase your depth of the footing, right? You have to increase your depth of the footing. Okay, so to be frank, it will be, if when you do the interpolation it will come. Okay, when you do the interpolation you will get the answer, right? So that how actual designs is done, that we will see in the next video. In this video I have just explained you that how your Excel sheet has to be designed. So in the next video we will see that how your actual design will be done by getting the values from the software. Thank you, learners.